Thanks to the organizers for the invitation for this really nice workshop. This talk will cover two papers, one that's a few years old and one that's just about a month old. I will acknowledge my collaborators separately in each of these two contributions. For now, I'd like to start by thanking my students, Tyler, Chloe, and Jack, for some of the slide material that comes up later in the talk. So I'd like to open this talk with a very high-level description of the traditional, what I think of as the traditional perspective on statistical tasks, in particular regression and classification, which is to treat them as essentially synonymous, but at the same time with a natural hierarchy in that regression is considered to be harder than classification. So what do I mean by all of this? More formally, if we think about most generalization bounds that take the uniform convergence approach, that is uniformly relating the empirical risk to the population risk, what we can typically do, and this is very nicely articulated in this seminal paper from the 2000s, that if we can evaluate the risk or minimize the risk by a continuous, typically convex, classification calibrated loss function, this type of a risk bound will directly transfer into a bound on the 0-1 risk, which is typically how we evaluate classification error. And a somewhat related consequence or property when we compare these tasks is that if we were to train our estimator on a regression task involving real-valued labels, then in most situations you can think of, the regression estimator would generalize out of the box to a classification task. In other words, if we think of our predictor f theta hat given by the regression estimator, if we have a good regression generalization property, meaning that on average f theta hat of x is pretty close to the ground truth function, which is f theta star of x, we would naturally expect to also get the corresponding classification task right, that is, get the signs of the two predictions right. So in summary, what we're saying is that traditionally the way we think of these tasks is, well, classification would generalize if regression generalized, and relatedly, we usually think of classification as somewhat easier than a regression task. So this talk is going to rethink this perspective in a couple of different ways. First, we are going to uncover the existence of specific problem settings in high-dimensional linear regression for which a regression task would not generalize, in the sense it would be inconsistent, but a classification task would, in contrast, generalize well. And here is the result in a picture for a specific example. So the orange label here represents the ground truth function. This is a very simple step function. And I will show you that there exists a specific procedure which would recover the estimated function, which is marked in green. And clearly, you can see from this very simple picture that this is a scenario that is very poor for regression. You see that most of the places, the green function is very far away from the orange ground truth. But it is actually a scenario that turns out to be quite good for classification. And in the first part of this talk, I'll make this setting much more formal.
So can I just ask?
Yeah, of course.
I think I just missed what you said on the last slide. So this is a situation where classification seems to be easier than regression.
Yes, but easier in a much stronger way. So I will get classification rates that do not follow from regression rates.
Oh, I see. I understand. Thank you. Got it.
Yeah, hope it made sense. OK. And in the next part of the talk, which will be a little bit shorter, I'll flip this problem on its head a little bit and ask the much tougher question of whether we can use data that was trained on a simpler classification task to shift and generalize to a much harder regression task. And somewhat surprisingly, we will see that in some cases, formalized in certain ways, this goal of task shift is in fact possible. So this talk will be situated in the regime of high-dimensional or over-parameterized linear models. And this is a setting that is simple enough to get the precise comparisons between tasks that we are after. It is also a setting that is complex enough due to the presence of high dimensions to find a rich variety of behaviors and the desired separations in tasks that we are after. I will begin by introducing the setup formally for both of the tasks that we are interested in. And interestingly, we're going to see some connections to this literature that has been mentioned in a couple of talks on benign overfitting of noise or harmless interpolation, despite not necessarily having label noise in the original problem. So let's start with our basic setting of regression. So this is just an additive noise model where my response label, which I'm denoting by Z, is going to constitute a linear combination of d-dimensional features, which I denote by phi of x, And theta star denotes my true parameter, or what I'm commonly going to call the signal, which is typically unknown to the learner, plus some noise of variance sigma squared. And as I said, this noise need not necessarily be there, but our results will hold both in the presence and absence of noise. I'll make some standard assumptions on my data model. I'll assume in particular that the features are centered, and I'll denote by sigma the covariance matrix of the features. And my theoretical results are going to assume that the features are either Gaussian or comprised of independent sub-Gaussian components. And accordingly, I'm going to assume that the covariance matrix is diagonal. In the case of Gaussian features, we can remove this diagonal assumption, but not otherwise. So my theory results are going to focus on this case. However, I am also going to provide corresponding illustrations of my main results in this kind of interesting case where I can actually have low-dimensional data X and have this lifted into a high-dimensional feature map. And this is always a scenario that you encounter, for example, in kernel methods. The specific examples I will use are the Fourier basis. And this is actually what's nice about these illustrations is because my data is one-dimensional, what it means is I can actually visualize estimated function fits and things like that and get a lot of intuition for all of the phenomena that I will describe. I will note that you can obtain corresponding theoretical results for this setting as well, but it turns out that the random matrix theory becomes a lot more technical. So as I mentioned, we'll operate in this very overparameterized regime where D exceeds N. And importantly, I'm not going to assume proportional scaling. I'm going to work in a very ultra-high dimensional regime where D significantly exceeds N. So concrete examples would be, for example, if D is polynomially scaling in N, maybe D is N squared or something like that. And in this setting, what we can see is very obviously that the linear system that we set up to solve for an estimated theta is underdetermined. So what this means is X in bold here denotes my data matrix, and Z denotes my label vector. And this linear system, X theta equals Z, will naturally have infinitely many solutions that achieve zero training error. In other words, these solutions interpolate the training data. So when I say interpolation for this talk, what I mean is precisely that theta perfectly fits the training data. So naturally, there's an identifiability issue that arises when you want to solve linear systems of this type, which is which interpolating solution do you in fact decide to pick? So for this talk, our solution of focus is going to be the minimum L2 norm interpolator. That is, we pick the solution that minimizes the 2 norm of the weights subject to this interpolation constraint. And accordingly, my evaluation metric for regression will be the mean squared error. This is the standard error metric according to which we evaluate regression. I simply take my prediction X transpose theta hat. I compare it to X transpose theta star. I look at the squared error. I take an expectation over the randomness in X. And I want this quantity to be as small as possible. And also, please stop me at any point if there are questions, especially in this beginning part of the setup. OK? So let's move on to our setting of classification. A lot of the notation here is going to carry over, particularly with my assumptions on the covariates and so on and so forth. The first main difference when we switch to classification is in my label model. So in regression, we had real valued labels and additive Gaussian noise. In classification, we now have binary labels. And we have this type of generalized linear model noise that people who work in high-dimensional statistics have probably seen something of this nature. And the idea is that y is going to be equal to 1 with a probability that is this link function g of X transpose theta star, and g is going to be a mapping between 0 and 1. So this link function essentially encodes label noise. And it's it encodes a diverse variety of types of label noise model. I could have no noise, in which case I would just look at the sign of X transpose theta star, and you can define a function g that would do that. You can also do like constant label noise, for example. And you can also do more complex types of noise, such as noise coming from the logistic model. We make a mild assumption here that essentially the expectation of g times 2g of z minus 1 is greater than 0. If this Hertz here had to look at the way you can think of this, is essentially what we want to say is that theta star actually affects the probabilities that we see plus or minus 1. So what this would rule out, for example, is just having 1 with probability half and minus 1 with the probability half, which is obviously a scenario in which learning is simply not possible. So this is a very mild assumption, very standard in the statistics literature. And as before, our solution of focus is going to continue to be this interpolator. The only difference is now we are interpolating binary labels. And it's worth noting that for these plus or minus 1 valued labels, we can rewrite the interpolation constraint as a type of exact margin constraint where we're achieving this margin of exactly 1 on the training data points. In this setting, the other major change when we go from regression to classification is the evaluation metric. So before in regression, we cared about the MSE. We wanted x transpose theta hat to be close to x transpose theta star in the squared error metric. Now in classification, we only care about getting the sign of the prediction right. Nonetheless, for both tasks, we'll define this concept of good generalization. So I'll use this word good generalization a lot throughout the talk. And all I will mean when I describe it is that we want statistical consistency, meaning that the error, whether measured through regression or classification, should go to 0 as n and d grow to infinity together. Yeah?
So you're going to get the solution from mean norm interpolation, but test on the right?
Yes. So my next slide is going to justify a little bit why I chose these specific solutions.
Can I ask also just a clarifying question? So just about your assumption that z and 2g minus 1 are correlated or positively correlated.
Yeah.
I mean, so that kind of sounds like at least some of the signal you could have learned with like a linear amount of samples. It kind of says that like the projection of 2g minus 1 onto like the linear functions, is like non-zero. And so,
right.
but you have like, you're explicitly kind of excluding that case. You want more data points.
That's a good point. What I would say this assumption, so z is at the level here of like the scalar quantity x transpose theta star. So you're right. Like what this assumption ensures, for example, is that I can learn the norm of like x trans. Like for example, I can learn something with the form theta star transpose sigma theta star. Like that's what I would be able to learn from samples very easily under this assumption. Learning the d-dimensional quantity of interest, which is theta star, is a lot harder. Does that kind of make sense? Yeah. Okay, thanks for all the questions. Okay, so let's ask this question at this stage of like, why did we pick the MNI estimator in particular to study? So the biggest reason, honestly, is that this is one of the simplest estimators to analyze in the fine-grained way that we want to compare these different tasks. However, I can come up with a lot of post hoc justifications for why I chose this estimator, and that's what's actually on this slide. So the first reason, the first thing we can ask is why the L2 inductive bias in the first place? So why are we picking these types of minimum norm solutions? And that has a very simple answer. We know from the last about 10 years or so of research that these solutions of a minimum norm inductive bias arise very naturally as a consequence of training models, linear models, with gradient descent algorithm. And this insight extends by this point to a variety of different types of loss functions. So I've only written the corresponding result for the logistic loss and the squared loss. Moreover, a result that we showed a few years ago is that, which I think is of independent interest, is that it turns out that these two solutions, for the log loss, you get the max margin SVM, and for the squared loss, you get the minimum norm interpolation, turn out to exactly coincide with a sufficient amount of overparameterization that is in these regimes where d is much greater than n. I'm not going to focus on these results too much in the talk, but I'm happy to talk about them offline.
Question.
Yeah.
How can all these results be independent of the structure of sigma?
Oh yeah, so there's a lot of details I haven't put on this slide. So really what I mean is sufficient effective overparameterization, and you're going to get like effective ranks of sigma. But yeah, this slide did not go into all of that detail. Okay, perfect. So roughly what we're saying is that this is a solution of focus that arises as the implicit bias of gradient descent on these pure linear models. A somewhat more tenuous connection to neural nets that we could make is if we trained the neural net in a layer-wise way. That is, we trained the nonlinear layers in one step and then the linear layer in the last step. This implicit bias of minimum norm solutions would also arise at the last layer from that procedure. And this is a common theoretical simplification that I've seen in the literature, particularly for analyses of things like feature learning and so on. Okay, so with my setup complete, I'm going to go ahead and turn to our first goal of comparing classification and regression. I'll pause at this point to see if there are any more questions. Okay. So I'll start by acknowledging my collaborators on this piece of work. So this started a few years ago, as I mentioned, through a collaboration at the Simons Institute. They had a really nice program on foundations of deep learning, I believe, in 2019, and this started around 2020, 2021. And subsequently, a lot of the technical insights were built on with Christos and Kay. So I'm very grateful to all of my collaborators for this effort. So just as a refresher, we can compare our data model, our estimator focus, and evaluation metric for both regression and classification tasks in a nutshell here. So for regression, we have the additive noise model. For classification, we have this kind of label noise model. In both cases, we're looking at this interpolating estimator, but the main difference is in regression, we fit real-valued labels, and in classification, we fit binary-valued labels. And the biggest difference, as it's going to turn out, is going to arise in the evaluation metric. For regression, we look at the test MSE. And for classification, we look at the test 0-1 error. And just to refresh the assumptions that I'm making for both the tasks, I'm going to assume this diagonal covariance. Like I said, the diagonalness can be removed for Gaussian data is needed otherwise. I'm going to assume this heavily over-parameterized regime. And importantly, I'm going to add in one more assumption into this work, which is one of low-dimensional structure in the ground truth signal, meaning that theta star is sublinearly sparse, and the sparsity parameter is given by t. So a bit of context here for why I brought in this additional assumption. It is well known that in high-dimensional linear regression, if we did not have an assumption of this type, learning would become information theoretically impossible. So in some sense, we need to make an assumption like this to make the problem well posed. So the question we're going to address here is, more concretely, are there ever situations under which theta hat CL, that is the classification estimator, would generalize well according to the 0-1 metric, where a corresponding regression estimator, which is theta hat regression, would not generalize according to the MSE metric? So I'll pause to let that sink in. But the idea is I'm going to define a common data covariance, a common ground truth signal model. I'll generate my data for regression and classification in these two different ways, get these two different estimators. And then I will ask this, what this enables me to do is directly compare these tasks and ask, does theta hat CL generalize in this metric, in a situation where theta hat regression would not generalize according to its own.
Just a question.
Yeah.
I mean, in a sense, in the regression, the kind of constraint you're putting on theta is L2, and your structural constraint is like an L1 constraint, right? So, if the answer of this is positive, it's just because your regression problem was set out to fail from the onset?
Yeah, so that's an excellent point. My next few slides are going to get into that a little more. You're right that I've set this up to be a setting. I'm going to make assumptions in the covariance that are going to kind of mitigate that problem somewhat. We're going to get to that in a little bit. But what we'll see is that the same problem that you describe of the inductive bias being mismatched is the case for both tasks. So what we're going to find is a separation in tasks. I'm not changing the inductive bias between these. So the L2 minimization pitfalls that you mentioned are going to be present in both tasks. So it's a more fine-grained difference. But yeah, great question. You're leading into my next few slides. So here's a bit of an obligatory related work slide about kind of just summarizing papers that have worked in problems in the spirit in the last few years. I especially want to call out the works by Bartlett et al. That I think have already been mentioned by a few other people, and also this nice follow-up work by Sigler and Bartlett that actually got a completely sharp control in the case of regression on each of the individual terms. So although I do not necessarily need label noise in either of my models, like my conclusions are not going to change regardless of whether I have noise or do not have noise, it turns out that a lot of the random matrix theory that was developed for this benign overfitting work is going to also show up in my analysis. And as I said, this kind of, since the linear regression work arose, there's been a lot of focus on analyzing these corresponding problems for classification. One other quick thing I'll mention here is that my results are going to be kind of situated in this ultra-high dimensional regime where D greatly exceeds N. And I'm going to be obtaining non-asymptotic error expressions for finite values of N and D. In general, this regime is distinct and arises different phenomena from what you would see in the proportional asymptotic regime where D and N are proportional. So you get completely different behaviors in each of these two cases, but there's been a lot of work in both. So at this point, I want to take a bit of a detour into the signal processing world to kind of establish what I think has already been asked by one of the audience members. What is the real issue with L2 minimizing solutions? Is it, and it turns out to have nothing to do whatsoever with overfitting noise. And this was an issue that was noticed very early on, like at least 30, 40 years ago, by the signal processing and compressive sensing community. So this community was interested in overparameterized learning from a somewhat different perspective. They wanted to look at ground truth signals, which had many different frequencies. You can think of frequencies as parameters in this analog. And they wanted to subsample or undersample this signal, kind of at below the Nyquist rate. And what that turns out to correspond to is exactly what we are calling overparameterized learning. And what ends up happening when you try to subsample your signal in this way and reconstruct it is precisely an overparameterized learning problem. You end up with an underdetermined linear system, and you need to find the right structural bias to recover your signal. So an example that I've kind of depicted here is from a very classical reference on this topic by Chen, Donahoe, and Saunders. And I'll explain a subset of these figures to tell you a little bit about what's going on here. So the signal on the figure on the top left here is essentially my ground truth signal measured in function space. And what's in the top right is essentially the signal in coefficient space. So I'm looking at the wavelet basis, and I'm looking at the coefficients of that signal in the wavelet basis. And you don't have to understand all of the axes in this figure. The most important thing to note here is that there are only a few non-zero components that are marked in black. So this is essentially, it turns out to be a 6-sparse signal, if you want the exact numbers. And then we can move on to look at what happens if we reconstruct the signal using what the signal processing community calls method of frames. This is really minimum L2 norm interpolation, so it's exactly what we are studying today. And you see something that's crazily bad. I mean, you basically see that if you squint really, really closely, you see that maybe there was a little bit of that signal that was recovered. But it's essentially completely attenuated. It's gone all the way down to 0. And importantly, this negative effect, this attenuation effect, has nothing to do with noise. There was no noise involved in the subsampling process in this problem. And of course, this naturally motivated the community to look at better inductive biases. Perhaps the most well-known of these would be the basis pursuit, which is just the minimum L1 norm. And this is just a bit of a reminder for why don't people like L2 minimization in these very high-dimensional settings. So this attenuation effect that I visualized for you in the previous slide turns out to be the most acute when I consider a data covariance that is isotropic. So what do I mean by isotropic? I just mean that the covariance of the data matrix is the identity. And intuitively, what that is saying is that all my features are kind of weighted equally. And the problem with L2 minimization is it sort of spreads out my recovered signal, or like theta hat has equally weighted components in all of the different features. So now we'll talk a little bit about, so the reason I wanted to talk about all this was to really motivate some of the data modeling assumptions I'm going to make this problem a little better posed. And in particular, we will now see that this attenuation effect can be somewhat mitigated or reduced if we introduce a type of anisotropy into the covariance model. And you can think of this anisotropy in many different ways. You can think of it as reducing the effective dimension of the problem. So our results are kind of pretty general, but for simplicity, I'm going to focus most of the results in the specific situation of a spiked covariance model, where I assume that my covariance is anisotropic in this very specific way, where I have a top set of eigenvalues or feature magnitudes equivalently that are larger, and and kind of a long tail of eigenvalues that has a much lower value. And I'm also going to make a further assumption that the signal, in fact, lies within the spike, meaning that my support of theta star is going to lie within these top S components. So in a little more detail, the spiked covariance ensemble is parameterized by the number of data examples, the data dimension, that is D, essentially the magnitude of the spike, which is what I'm calling S, and also the ratio between this higher level eigenvalue and this bottom level eigenvalue. So a fact that you can actually show for this setting is that it turns out that noise overfitting is never an issue for this model. And if you are familiar with the results of Bartlett et al., you can kind of see this as a corollary of some of their results. The basic idea is that you kind of have this long tail of lower level eigenvalues, and that kind of hides the noise in a particularly nice way. But the more important thing that I'm going to focus on for the purpose of the talk today is that intuitively, this kind of ratio, what we really want is for it to be as large as possible, because if the ratio is larger and if the signal lies within this kind of spike, then what it means is that we're effectively prioritizing those particular coordinates of the data covariance, and we're ensuring that the signal will get preserved. And I'm going to show you a few simulations that show that, in fact, this reduces that attenuation effect. So there are a lot of assumptions that I've added into the model here. I want to pause to give a little bit of context for why I have made these assumptions. So if we think about, for example, the Gaussian mixture model, which is another popular model in high-dimensional statistics, I have covariates that are just y times mu plus z, where z is kind of like covariance noise, and y is like my label vector. And it turns out that if you look at the unconditional data covariance of this model and you diagonalize it and look at the eigenvalues and so on and so forth, you can actually compute this ratio quantity effectively. And what it turns out to correspond to is the magnitude, the L2 norm of the signal parameter, that is mu squared, divided by the variance of the covariate noise parameter. So it kind of becomes like a signal to covariate noise ratio. And if you visualize like a Gaussian mixture model in a picture, then you'll expect that you want the signal magnitude to be large, which means the mixtures are better separated. And you also want the covariate noise to be small, meaning that these kind of point clouds would not blend together too much. So this is just a bit of intuition to kind of explain like why we want this ratio to be really large. And invariably, we're going to see in the results on the next slide that the higher the value of this ratio, the better both generalization guarantees will end up being. Just to mention a very quick, more high-level kind of justification for anisotropy, it also turns out that you can kind of do these purely empirical studies where you look at the last layer of a neural net, you look at the features that were learned by the neural network, and you can actually estimate these spectra, and this is usually something that is reasonable to do without too much error. You end up seeing this kind of anisotropy. It looks a bit different. It's more like a polynomial or a power law decay in the eigenvalues. This is also something that we can study in our framework, but it becomes a lot more complicated. OK, so hopefully people understand why we're looking at anisotropy in this setting. OK, so let me just get to the first main result that I want to present today. And in a nutshell, what we are going to show is in this spiked covariance ensemble, we can find 3 regimes that dictate whether classification or regression would generalize or not. So the way this result is going to be structured is I'm going to have figures on the top visualized on 1D data, where we're going to see what the tasks look like in function space. And I'm going to write the main result down here. So we'll start with the somewhat classical regime, where the ratio between the top and the lower eigenvalue greatly exceeds d over n. And it turns out that in this setting, regression will generalize well, and therefore classification would also generalize well. You can get this, for example, by looking at the results of Bartlett et al., but this was actually, if you removed label noise from the process, this was actually well known. I mean, you could just plug in a generalization bound based on like the Rademacher complexity, and this is the conclusion you would get. So this is the setting in which regression generalizes, and in some sense, we kind of knew this. Now in the middle regime, what we uncovered in our work is the existence of a new regime where this ratio between the top and the lower eigenvalue is much less than d over n, but much greater than square root of d over n, in which regression would not generalize, meaning we can provide a lower bound on the regression MSE in the setting, but we can show that the classification error would in fact go to 0. So in this regime, classification generalizes, but regression does not. And finally, our analysis technique is tight, because we were also able to show that if the ratio was much less than this new threshold of root d over n, we end up in this kind of scenario that is catastrophic for both of the tasks, meaning that neither regression nor classification would generalize. A quick and somewhat provocative comment that I want to make here is that I'm not aware of any generalization bound applied out of the box that would predict this type of separation. But I also want to mention that there's this nice work by Negria et al. That actually does start to examine how we can get generalization bounds for interpolating solutions. And I'd be happy to talk more about that offline.
So can I ask, what's the role of S in this picture? Your sparsity parameter?
That's a good question. I'll get to some explicit rates in the next few slides that will hopefully answer that question. It turns out that because S is sublinear in N, this broad conclusion does not change. But I'll make that more concrete in a bit. OK. So now I kind of want to get into what really underlies this separation. And I'm going to illustrate the main idea for a one sparse signal, although this, again, extends to t sparse signals that lie inside the spike. So the first important step here was that we provided a novel decomposition that is different from the bias variance decomposition. And what it does is it breaks up the error into a feature-by-feature analysis where we look at a signal-dependent term and a noise-dependent term. So formally, what we're going to do is we're going to measure the fraction of the true signal component that survived. I'm going to call this SU. This is just theta hat 1 divided by theta star 1. And I'm going to look at a proportion of like false or junk features and what their contribution is to the overall estimator. And this is going to be defined in terms of a standard deviation type quantity, which I'm calling contamination. And it's actually kind of an elementary derivation in the case of regression that the MSE would be 1 minus SU squared plus CN squared. This is not difficult to see. And essentially what this tells us is that for regression consistency, for regression generalization, we need the survival to go to 1 and the contamination to go to 0. And what you can do with this is you can actually plug in this alternative decomposition and recover the results of Sigler and Bartlett, not only for this spiked covariance, but for many other anisotropic ensembles. The specific rate that you end up getting is matching upper and lower bounds of the form d minus s divided by d minus s plus nr squared. And what this, if you stare at this a little bit, you'll see that this automatically implies the desired generalization result if the ratio r greatly exceeds d over n. And you can kind of stare at this simple expression and kind of see that. OK. And perhaps more interestingly, this new decomposition enables us to control the classification error in a much sharper way than we would be able to do if we just did a bias variance decomposition. And what we can do is get a more fine-grained expression for the classification error. So this expression uses Gaussian data, which is why you kind of have this half and this 1 minus 1 over pi and things like that. But you can get a more gentle upper bound in the case of sub-Gaussian features as well. So the most important thing that you can see from this expression is that for good generalization, we want this whole thing to go to 0, which means that we want this thing, tan inverse of SU by Cn, to go to pi over 2. And essentially, what that means qualitatively is that we want the ratio of the survival to the contamination to grow to infinity. And what that allows us to do is look at these very delicate scenarios where maybe the signal does not survive, meaning that SU goes to 0. But at the same time, contamination goes to 0 at an even faster rate. And therefore, the ratio between these two quantities would then grow to infinity. And that's what we end up doing. We end up plugging in these bounds. And we get this precise type of rate on the test 0-1 loss. And now you see there's still an r up here, but there's a square root of d over n, d minus s over n. And because s is sublinear in n, what we end up seeing is that this goes to 0 and it goes to infinity if the r is much greater than root of d over n. So don't worry if you didn't follow all of the math on the slide. The basic idea is that we can allow these situations where the signal attenuates all the way to 0, as long as it does so at a slower rate than the rate at which the contamination part goes to 0. So that's the basic idea in a nutshell. I'll include one more slightly more technical slide that talks about how we actually analyze these two quantities. So the contamination part turns out to be quite simple. You can end up making a specific connection to the analysis of benign overfitting of noise, specifically the variance terms in Bartlett et al. For the spiked covariance, this becomes a particularly simple calculation. You just get S over n plus n over d. And clearly in our ensemble, this is always going to go to 0. The survival analysis is perhaps the more interesting part. You can kind of write this expression directly. So we're using the closed form expression of the MNI in this very first step. Just a bit of new notation. U1 is a standard normal vector. And I'm going to do a type of leave one out analysis. So I need to do this because y depends quite intricately on xx transpose. So this is just a Woodbury identity, and I get all of this stuff here. I'm not going to go into all of the random matrix theory that goes in here, but the rough idea is that once we do this, we can, in the one sparse case, things become relatively simple, and we can actually plug in random matrix theory results on each of these quantities and use the fact that y is independent of what's in here and u1 is independent of what is in here. And ultimately, we get this kind of interesting condition on the survival, which relates to the top eigenvalue times the trace of the leave one out matrix inverse divided by 1 plus that. And there's a kind of tension that ends up happening where like the trace of this thing is typically going to decay with n and d. But if lambda 1, if the spike is kind of large enough, this could cancel out that effect in a nice way. So ultimately, what we end up seeing in the setting is like in the classical regime where we know regression works, the survival factor can be shown to go to 1. In the intermediate regime that we found, the survival will very much go to 0, and that's why regression doesn't work. But it turns out to go to 0 at a slower rate than the contamination factor, and it turns out that classification would generalize in this setting. And finally, in the last regime, survival goes to 0 at a faster rate than Cn, and therefore neither task would work. And this can all be generalized to t-sparse solutions, and this part and multi-class classification, the details here become a lot more technical.
So can I ask for just a second? So just to connect to, I think, what Elvis was asking before, if I remember right? Like, if you were to just do some kind of thresholding on what you learned for your regression theta, you know, I think you're like maybe a way of restating some of this, or maybe I don't see something, is that there's like some threshold, and if you just zero out everything below the threshold, you will kill the projection onto the contaminated interactions.
Oh yeah, absolutely.
Keep only the survived interactions, and that would make the classification and the regression closer. But that's kind of like a L1 idea anyway. So that's
kind of what I'm going to touch upon in the next part of the talk. Like that's how we're going to go from classification, like what you just described. The surprising thing is that it works for L2 minimizing solutions. Like as you said, these types of ideas are usually applied to an L1 minimizing solution, and we're showing that you can extract quite a bit out of L2 minimizing solutions. Okay, I want to end this part of the talk by zooming out a little bit and asking like how much of this was specific to linear models, to the assumptions that I made. I think this is a very open and fertile direction. I'll call out a few papers that I think either showed these types of separations in more complex settings or use this feature by feature analysis, which is really the main thing that I'm kind of advocating for. So I'll mention this nice work by Radhakrishnan, Belkin, and Uller, who looked at infinitely wide and deep neural tangent kernels. So these were not neural networks. But what they showed were some explicit connections to local methods or non-parametric methods. And they actually found situations under which this attenuation happens in the case of regression, but it does not affect classification performance. So this was not this was like a neural tangent kernel paper rather than a neural net paper, but I think it had some very interesting insights. I also want to mention this work by Glasgow, Wei, Wouters, and Ma, who looked a little more closely at relationships between generalization and uniform convergence. And they had some results that were novel also for the linear model, but they also looked at this specific signal model of a ground truth quadratic XR function. And they sort of found similar phenomena. They found that this attenuation happens. They didn't look at regression, but they showed that this was a situation where you would not get generalization from a generalization plot. And there's also this nice paper by Ohad Shamir, where they showed that, for example, if you bring in model misspecification and you try to still do a linear model analysis, it hurts regression performance a lot, but classification not so much. So there are many ways in which you can uncover these separations. As a last point, there's this, I think, this is actually prior to our work, but there's this very interesting work by Zhe-Yuan Alan Zhu and Yuanqi Li, where they looked at this like full-blown, I think, shallow neural network. And they compared clean and adversarial training. And they found like that feature by feature analyses where the features of the neurons actually yielded a lot of insight into what was going on. So these are all papers that I think form the starting point for trying to come up with these separations. But again, there's a lot of open directions here. OK. So probably for the next 10 minutes of my talk, I'm going to move on to this kind of new setting of task transfer. The techniques are going to build a lot on what I already presented, so this is going to be a lot shorter. I'll pause for any more questions if there are any. OK. So this is joint work with my students, Kuo and Tyler. And I owe a lot to them for this particular part of the talk, because they not only solved this problem, but they actually conceptualized this very problem formulation. So they came to me one day and asked this kind of, I think, unusual and intriguing question of whether you can kind of, we saw just now that there are some aspects of generalization that may be unique to classification. Now we ask the reverse question of whether we can use model weights trained on a classification task to generalize to a more complex regression one. So formally in our setting, if we look at the classification estimator theta hat CL, we ask whether we can use these model weights to generalize to the more complex regression task. And more formally, we'll ask this question in a couple of ways. We'll first ask whether this model generalizes in a zero-shot way. That is, if we just apply it out of the box, will it generalize? The results are going to be a little more negative here, but we'll actually see that it's not as bad as you might expect. The second question is, can we minimally post-process theta hat CL using a very, very tiny amount of regression data to achieve generalization on this regression task? So I'll pause for a minute to see if the goal is clear to people. OK. So my students were interested in this problem formulation. They made this kind of high-level connection to in-context learning in large language models, where the belief is that there's some sort of maybe not only a covariate shift or a ground truth shift, but also a fundamental task shift. Because when we think of LLMs, they're doing like next token prediction, and then we see that they can suddenly do something like linear regression. I was intrigued by this. I wanted to first think of other problem formulations that are related in spirit to this type of goal. The first one that is kind of obvious, and we already heard a manifestation of this talk of this problem in the morning, was this idea of transfer or multitask learning. There's way too much literature on this topic for me to possibly summarize on one slide. The main thing I will mention is that this problem formulation of transfer learning usually does not involve changing the nature of the task. What we usually do is see whether we can transfer between two different regression tasks or two different classification tasks. We do not change up the nature of the task itself. What we do is we either change the data distribution, the covariate distribution, or the ground truth model. The more related problem formulation in terms of the math, underlying math, is this, again, comes from the signal processing literature, and it's the setting of one-bit compressive sensing. So this is exactly our zero-shot formulation, because in this literature, what you're typically doing is you're measuring your signal along these various linear measurements, and then you compress it to 1 bit, meaning you take the sign of the measurement. So we have binary data, and we're effectively training on those binary labels, and ultimately we want to estimate theta star in some meaningful way. In some sense, as is also turns out to be the case for our problem setup, you do lose information about the magnitude of the signal. And the guarantees here are usually in the direction of theta star. And the estimators usually involve L1 minimization. We are going to show that we will get a similar type of guarantee in the zero-shot setting. It's actually a very intriguing point that in this literature, there are some settings under which you can even estimate the magnitude of theta star in a zero-shot way. But here, the measurement matrix usually needs to be designed in a very clever way, and this is not something we can do in a learning setting. So I'm going to be relatively more high-level for the last part of this talk. I'll just present the main results for both a zero-shot and few-shot setting. So starting with the zero-shot setting, I'm going to continue to assume that the signal lies within the spike. And we can extend these survival contamination definitions for the t-sparse setting for the purpose of these results. I can again look at each of my components in the support and look at theta hat divided by theta star. And I can also look at my contamination, which sums up everything that is not in the support. And I can get a limiting characterization of the regression error under all the assumptions that I have set up. I don't have any contamination because that goes to 0. And I just care about tracking the amount of survival in each of these cases. So in the first two regimes where regression did not generalize, this is not a very interesting, this is not a very well-posed goal, because these were settings in which even if I took the estimator intended for the regression task, it would not generalize. So, well, why should I expect an estimator trained on a classification task to do any better? And that's what ends up happening. You have this attenuation all the way to 0, and you end up getting something like the null risk for the problem. The interesting regime is the third one. And what we can show in a very precise way is for these, as a result of using classification labels and not regression labels, you can show that this attenuation is a very precise expression that depends on root 2 over pi and the signal magnitude. One way of interpreting this, which is a bit narrow, is that this would imply generalization only for the pre-specified signal magnitude. I think a better way of interpreting this result is that what it does show is that we're able to recover theta star up to this direction, up to this scaling factor, which may be a meaningful result. So now I'll end this talk by moving on to the few-shot setting. And now the idea is that we have this theta hat CL, but we are allowed to process it in very minimal ways. and possibly using a very small amount of additional training data that is intended for regression. So that's why I'm calling it a few-shot problem. And here, interestingly, the picture becomes a lot more favorable. And this is essentially because, as we've kind of been seeing, the coefficients in terms of absolute magnitude suffer from this attenuation effect. It turns out that a lot of information about their relative magnitudes is preserved. And what this means is I can do a very simple and classical type of support recovery procedure to identify the top T components. So this is, of course, using the sparsity assumption, but it turns out to work in quite a few situations. So I'll do this kind of support recovery procedure. I'll recover it, and then I can do any number of things on my few-shot labels. I can just use a least squares estimator or do ridge. And now I'm underparameterized because typically T is going to be very, very small. So this is just an informal result. Come talk to me if you want precise conditions under which this works. But the kind of cool thing is that we can show that this recovery procedure is successful for a pretty wide range of covariance matrices, and I'll kind of illustrate that on the next slide. As an immediate corollary of support recovery, we get what you might expect from a variable selection guarantee, which is that you get rates. Either you can exactly generalize if you had noiseless regression data, or you end up getting rates of the underparameterized nature, like T sigma squared divided by M, where M is the number of regression labels. So either way, this is a very positive result, and it's showing that non-trivial task transfer does indeed occur. So the last result that I'm going to show you for this talk is a depiction of what this few-shot procedure really looks like. And what we're going to see in a nutshell is that this succeeds in all of the three regimes, including isotropic covariance, which I think the last one was interesting to me. So the plots here kind of show the proportion of estimated signals. So I have theta hat CL as a function of the index. And this is the case where you have minimal attenuation. You would expect things to work. This is the case where you have attenuation going to 0, but at a slower rate. And this is the case where you have very fast attenuation. So this is actually isotropic covariance. And the kind of cool thing is that we can show for a finite value of n that the support would be correctly recovered in all three of these cases. And if you then kind of move on and look at the resulting error of the post-processing estimator as a function of m, you can kind of see effectively that this post-processing estimator generalizes really well in situations where not only the original classification estimator would not, but even the original regression estimator would not. And that's kind of what we see. And again, this kind of, what I think this shows you in a nutshell is that despite the pitfalls of the L2 inductive bias in many of these settings, particularly in regime 1, it still contains useful relative information about features, and we can still do like this type of feature selection and get guarantees, even from misspecified inductive bias. So I'm going to end the talk there with a couple of very broad takeaways. The first is that in the first part of the talk, we saw that there exist these high-dimensional regimes in which classification can generalize even though the corresponding regression task would not. And this insight was somewhat specific to the L2 inductive bias, but I think it's interesting to see whether it holds for other inductive biases as well. And in the last part of the talk, we saw that this kind of survival contamination perspective, like this feature-by-feature analysis, can be used to post-process an estimator on classification data in a very minimal way. So it's just a very lightweight support recovery plus training procedure to generalize on the more complex regression tasks. So in summary, models trained on a classification task contain useful information to generalize to a regression task. I'll close this with just a very broad summary of things I'm currently excited about and thinking about. I'm very interested in distributional robustness. I'm also interested in understanding data augmentation. And I presented most of my work up until this point has been on linear models and kernel methods, but increasingly I'm interested in feature learning as well. So with that, thank you for your attention and all the really nice questions. I'm happy to take more. And these are just some references for all the work.